Okay, so we are finally ready to start talking about quantum algorithms, and in this lecture I'll talk about some of the building blocks that go into making up quantum algorithms and how they were used in some early quantum algorithms to demonstrate the power of quantum computing. So let's see. Last time we already talked about reversible computation, classical reversible computation, where we said, suppose you have a classical circuit that on input x computes c of x. And for now, I'm just going to talk about the case where c of x is Boolean, so it's just a single bit, just for simplicity. So then we said that there's a classical reversible circuit which takes as input x, an answer bit b, as well as a number of work bits, which are all initialized to 0. And then what this reversible circuit does is it spits out x unchanged. It also leaves the work bits in a clean state. So they are also in the 0 state. And it XORs the answer c of x into this answer bit b. So the output bit becomes b XOR c of x. So it toggles the bit b. So in the case that b is 0, then this answer bit is exactly c of x. Now, the other thing we said is that if we start with such a reversible circuit, we can also implement it using quantum gates. And so we get this unitary transformation u sub c, which in the case that the input bits happen to be classical in these basis states, then the behavior is exactly the same as we had before. Except, of course, now, since U is a unitary, it's a quantum circuit, so it can take as input a superposition of inputs. So for example, if we give it as input the superposition sum over all x of alpha x, x, and then b is, let's just say the input bit is always b, and I'll suppress these, the work bits, then the output is sum over all x, alpha x, same amplitude, input string is the same, and the output string is b XOR c of x. So you can compute in superposition this way. Now, this is one of the basic primitives for quantum computation, the fact that we can compute anything that we can compute classically, we can compute in superposition. But this is not yet enough. We need one more ingredient, and the crucial ingredient turns out to be the Hadamard transform. So remember what the Hadamard transform is. It's a transform on a single qubit, which maps 0 to plus and 1 to minus, and where plus, of course, is 1 over square root to 0, plus 1 over square root to 1, and minus is 1 over square root to 0, minus 1 over square root to 1. That's the Hadamard transform. That's our transformation. But now we can also perform this Hadamard transform on 2 qubits. So now what happens if we perform it on 2 qubits? Well, of course, what we'd have is 0, 0 would get mapped to plus plus, which turns out to be 1/2. Well, what is it? It's 1 over square root to 0 plus 1 over square root to 1, tensored with 1 over square root to 0 plus 1 over square root to 1, which is just 1/2 0, 0 plus 1/2 0, 1 plus 1/2 1, 0 plus 1/2 1, 1. So what it does is it takes 0, 0 as input and outputs an equal superposition over all the 4 inputs. And now you can work this out for all the other input strings, all the rest of the 3. Let's just work it out for 1, 1. So what does it do? It outputs minus minus, which is 1 over square root to 0 minus 1 over square root to 1, tensored with 1 over square root to 0 minus 1 over square root to 1. And what's that? Well, that's a half 0, 0 minus a half 0, 1 plus a half 1 0, sorry, minus a half, 1 0, plus a half, 1 1. So to understand this sign pattern, so basically, you should check that all the 4 classical strings get mapped to a superposition of zeros, 0 0 0 1 1 0 and 1 1, with amplitudes. All the amplitudes are plus or minus a half. So the only difference is what the sign pattern is. And to understand the sign pattern, you have to realize that each of these Hadamads maps 1. When you start with 1 and end up with 1, you get a negative sign. So this sign pattern ends up being the parity of how many 1-to-1 transitions there are. Now, if you want to write out the unitary transformation, you take the tensor product of this 2x2 matrix with itself, and if you remember the rules for doing that, you would just fill in 1 over square root 2 times this matrix in the upper left, so you'd get half, 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 minus half. And the same thing here, you'd get half, 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 minus a half. Same thing here, half, 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 minus a half. And then for this thing, what you're doing is since this entry is minus 1 over square root 2, you'd be multiplying this matrix by minus 1 over square root 2. So you'd get halves, but you'll also change signs. So you'd get minus a half, minus a half, minus a half, and a half. That's your Hadamard transform on 2 qubits. Similarly, you could do a Hadamard transform on 3 qubits. And you'd get an 8 by 8 matrix. And you'd be mapping, for example, 0, 0, 0 to an equal superposition. So 1 over twice square root 2, 0, 0, 0, so on up to 1, 1, 1. So there'd be 8 such possibilities. And again, you'd get a different sign pattern depending upon what string you started from. So make sure you work through this to understand, what this pattern looks like. Okay, so one thing you realize as you do this is what the Hadamard transform does is it starts with a classical string on the left, one of the basis strings, and it gives you a superposition over all the 2 to the n bit strings. So this is a very powerful thing, and it's a very important thing in quantum algorithms. It's a very important principle. So now let's try to understand what happens when we work with n qubits as n tends to infinity. So what happens? Well, so now we have n qubits. Let's say they were all initialized to, we start with each of them in the 0 state, and we put them through the Hadamard circuit, where each of them is going through a Hadamard gate. What's the output? Well, the output is clearly the plus state on all the qubits, which is equal to what? Well, I claim that it's just going to be the sum over all n-bit strings. So remember, this is how we denote the n-bit strings, where each such x has equal amplitude, and the amplitude is 2 to the n over 2. Right? Because we'll get a 1 over square root 2. How did we get this? Well, this is 1 over square root 2, 0, plus 1 over square root 2, 1, tensored with itself n times. Right? So it's a tensor product with itself n times. So another way we denote this is by just saying 1 over square root 2, 0, plus 1 over square root 2, 1, and then in the exponent we just put down this notation, tensored with itself n times. And now if you multiply these out, what do you get? Well, you get, depending upon which choice you take from each of these terms, you get some n-bit string, and what's its amplitude? Well, you get 1 over square root 2 times 1 over square root 2 n times, which is 1 over 2 to the n over 2. Okay, but now let's try to understand what happens if you start with some u equal to u1, u2 through u sub n. So let's say those are the n bits of u. So what happens when you perform the Hadamard transform on this? So let's say, what's our notation for this? It's H tensored with itself n times applied to u. So now, what do we get? Well, I claim that what we'd get is still the sum over all x of length n of x, but now in front of each of these x's we have its amplitude is 1 over 2 to the n over 2, but with either a plus or minus sign. So when do you get a plus sign and when do you get a minus sign? Well, you get minus 1 to the u dot x, where u dot x is u1 times x1 plus dot 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 plus un times xn. So remember what we already discussed before. The only time you get a minus 1 sign is when your input bit, so these are input bits now, they are u1, u2, so on up to u sub n, and our output bits are now x1, x2, and so on up to x sub n. Okay. So when do you get a minus sign? Well, only when the input bit is equal to the output bit equal to 1, right? So u dot x is counting how many such minus signs you get. And then when you take minus 1 to this power, it tells you whether you get an odd number or an even number of minus signs. And so your overall phase is negative if and only if you get an odd number of minus signs. Right? So, for example, if n equal to 3, u equal to 1, 1, 1, x equal to 1, 0, 1, then what would you get? Well, you'd get u dot x is equal to 1 times 1 plus 1 times 0 plus 1 times 1, which is 2. And so minus 1 to the u dot x divided by 2 to the n over 2 would be minus 1 to the 2 divided by 2 to the 3 over 2, which is 1 over 2 to the 3 over 2. So that would be the amplitude of x, which is this, if you start with the input being 1, 1, 1. So now, here's the new primitive that we have. The new primitive that we have is that we can start with any old superposition psi that we want. So we set up some superposition on n qubits psi. Then we apply the Hadamard transform. So we get as output some new superposition. So psi might be the superposition sum over x, alpha x, x. Psi hat is some new superposition sum over x, beta sub x, x. Okay, so this is sum over x, beta sub x, x. And now what you do is, now you perform a measurement. And you measure. And so you see some y, so the output of this is some y with probability beta sub y magnitude squared. So this is our basic primitive in quantum computation. We call this Fourier sampling because, well, we'll see this later. What we call it Fourier sampling because the Hadamard transform is really the Fourier transform over the group z sub 2 of addition mod 2. Okay, but that's not the important part. That's just a name. The important part is we have this primitive, which is set up any superposition psi. So create some superposition psi. Now perform the Fourier transform or Hadamard transform. on these n qubits and then measure. What you have sampled from is this probability distribution. And this is called Fourier sampling. What we want to say is that this is a very powerful primitive, because without access to quantum, a quantum circuit, which is doing exponential work in figuring out how these amplitudes alpha x interfere to give you the betas, you'd have a very hard time trying to sample from the same distribution classically. Okay, so, but how do we make sense of this? How do we find, what does this primitive really help us do?